In this video, I'm going to talk about the analysis of covariance, starting as usual with an exploratory data analysis and the to be followed by the frequentist and the Bayesian model fitting. The codes and data to run this analysis are in the website. This is one of the chapters of this. This is one video associated with one of the chapters of the book that I published in 2023 with Oxford University Press. So let's first start by explaining the goal of the analysis of covariance. In chapters 4 and 5 and videos 4 to 8, I explain particular cases of the general linear model when the mean of the response variable, mu of y, was related to either one or several numerical explanatory variables or with one or several categorical explanatory variables with either one or two or more levels. So the analysis of covariance, in the analysis of covariance, the mean of the response variable is related to both one or more numerical explanatory variables and one or more categorical explanatory variables. So the statistical model, as usual, is that the response variable follows a normal distribution, since this is a special case of the general linear model, with now the mean of the response variable is related to the numerical explanatory variable x by a linear model defined by the intercept beta 0 and the slope beta 1 with the case, since we now have at least one categorical explanatory variable, either the slope and or the intercept can change depending on the level of this categorical explanatory variable. Let's see that in an example in a second. The analysis of covariance was developed by Ronald Fisher, as many of these analyses, as a way of controlling for the effect of a numerical explanatory variable so as to improve the effect of chancing of detecting differences between levels of a factor, the experimental factor that was manipulated in a design experiment. So whenever there is more than one explanatory variable, as explained in the previous video about the factorial ANOVA, their effects on the mean of the response variable mu of y could be either just additive or can be additive and interactive. So the interaction in the analysis of covariance is reflected by the fact that the slope that determines the effect of the numerical explanatory variable x on the mu of y, the mean of the response variable, differs depending on the level of the factor or categorical explanatory variables. So there are, in the simplest example, there are four possible cases. Let's see them. In the first, both the intercept and the slope for the two levels of the categorical explanatory variables are identical. Therefore, there is a single universal relationship between y and the numerical explanatory variable. This is the simplest possible case. In the second case, the slopes for the two levels of the categorical explanatory variables are the same, but there is a difference of intercepts. So there is a universal relationship between y and the x, the numerical explanatory variables, but the mean value changes because there is a difference in intercepts. In the third case, which is conceivable, there is a common slope, there is a common intercept and difference in slopes between the two levels of the categorical explanatory variables. In this case, there is no universal relationship between the numerical explanatory variable and y, since the slope changes depending on the level of the categorical explanatory variables. And in the fourth case, both the intercepts and the slopes are different depending on the levels of the explanatory variables. In cases A and B, we had additive effects of the explanatory variables because essentially the slope is the same. The slope between y and x, the numerical explanatory variable, is the same. The effects are just additive. And in cases C and D, illustrated here in this slide, we have interactive effects between explanatory variables. So let's import the data. The data concerns, the goal is to analyze whether the size of the cell, the diameter of bacterial cells, is affected by glucose after controlling for the culture concentration. So we have three variables: diameter, which is the response variable, concentration, which is a numerical explanatory variable, and glucose, yes or no, which is a categorical explanatory variables. The first question is whether these variables are related. So here I show two plots of the diameter against concentration. We see roughly showing a smooth line for each of the two levels of glucose, yes and no, and we see overall that we have a negative exponential relation, a nonlinear, a negative exponential relationship that differs depending on the level of glucose. When I now plot, in order to linearize the relationship, the negative exponential relationship between diameter and concentration, I obtain plot them in log-log space, and this roughly shows a linear relationship between the two. So the variables are related, yes. Concentration does not have a slope of 0 whenever concentration changes, diameter changes, declines, and the effect of glucose is apparent in these two plots, since there is no single relationship depending on glucose, but the relationship changes for glucose no and glucose yes. So the probability distribution, we are going to try both the normal and log normal, and we see that either distribution will do pretty well. So let's keep it normal. So this is important because the relation between diameter and concentration is only linear in the log-log space. I'm going to center the numerical explanatory variable to help in parameter interpretation. This was explained in the videos in a previous video when we talked about multiple regression. Please look at it. So we fit the model in which we have a linear model, the log of the diameter, not the diameter, the log of the diameter, because this is we need to linearize the relationship between diameter and concentration, log concentration in this case. And here we have the single effect of concentration, the single effect of glucose, and their interaction. This is a shortcut way of writing this in R. So the model is fitted as usual. We have the residual standard error, which raised to the square is an estimate of the variance of the response variable. The model explains 93% of the variation of the response variable. And so for glucose, the level of reference, we see here glucose has two levels, no and yes. We see here yes, therefore glucose no is the reference level. We can write an equation relating the diameter of relating the mean of the log diameter. This is the intercept for the reference level. This is the slope for the concentration. This all refer to the reference level. And for glucose, yes, now we have a differential of intercepts, which happens to be positive in this case. And here we see the interaction between log concentration and glucose, yes. Therefore, this is a difference of slopes. So in order to write the equation for glucose, so here we have the equation for glucose no, and here we have the equation for glucose yes, for which we need to add the differentials of intercepts to the intercept of the reference level, and we need to write the differentials of slopes to the slope of the reference level in order to obtain the equation for the other group. So we see that the interaction here, these differentials of slopes, does not happen to be statistically significant. I highly recommend writing up these equations to make sure that you understand the meaning of the fitted parameters in the models. So the package Broom allows to gather the usual input for the residual analysis. Now we have the 5 plots relating the residuals to the fitted values, identifying with dots for glucose no and with triangle for glucose yes. We see a more or less random scatter along this in this plane without any trend. There may be 2 points, just 2 points, which happen to be this and this one, that have larger residuals than the rest of the points. So this should not concern us too much. When plotting the residuals against the numerical explanatory variables, we see a random scatter without any trend, as it is a sign of a good fitting model. And when we compare the residuals with the explanatory variable, categorical explanatory variables, we see that the median of the residuals are both similar and close to zero, and that the variation of the residuals, as denoted by the width of the box, is not equal, but not too different between the two plots. We see that the overwhelming majority of the points are very close to the line of the perfect fit. Only 2 points, certainly these two are off on the lower tail of the distribution. So there is 1 point that probably has a large influence on the fitted value of the parameters. We could refit the model without this point and see if it makes any difference. I refer to you to previous models, to previous videos where I explained and did this refitting of the model without one of the parameters. To communicate the results, we obtain, as usual, the table with the parameter estimates and the 95% confidence intervals. And even better, the conditional curve obtained by the package GG effects. And so here we have a set of values for glucose no, for the centered log concentration. Okay, these are 2 standard deviation below the mean. These are 2.5 standard deviation above the mean, and the predicted values for glucose no and for glucose yes, and with this we can obtain the following plot that showing the fitted curves and the actual data, showing the pretty good fit of the model, which is of course related to the very high R square that I alluded before. Now, for the Bayesian model fitting, let's recall the fundamental statistical model of the analysis of covariance that I was explained before. Let's recall again the fundamental equation for the parameter estimation in Bayesian statistics, where we had at the left the posterior distributions of the parameters given the data is proportional to the likelihood of the data given the parameter values times the prior distribution of the parameters. This model has 5 parameters. The 5 parameters being the slope of the reference level, the intercept of the reference level, the slope of the reference level, the differentials of intercept, the differentials of slopes, and the variance of the response variable given the data. So this is the likelihood, and these are the priors. So the model then has 1, 2, 3, 4, and 5 parameters whose priors we need to define. So let's use as usual the very helpful command get prior of the package VRMS to find these parameters, and let's define here 2 sets of priors. I'm going to call them weak priors and strong priors. The weak priors are less scattered. We'll see that in a second in the slide, in the slope. So these are the weak. These are in continuous line. We have the weak priors. So it means that we have we expect larger possible scatter of values for the weak priors for for each of the parameters, and for the strong priors we have a smaller scatter, narrower. We have more information for the stronger priors than for the weak priors before seeing the data. So what I'm going to try to see is whether there is an influence of the priors, here arbitrarily defined, in the fitting of the model. So our Bayesian model for the weak priors is that we have the basic statistical model that we have been discussing, the family while Gaussian. Here we identified the set of the prior that we want to define, either the weak or the strong, the change, the warm-up. This was discussed before and need not be repeated here. So let me show the summaries for the weak priors and the summary for the strong priors. And let's compare the marginal posterior distributions of all parameters for each of these two sets of priors. Let's first realize that the models, both models seem to have converged, as the R-hat statistics are all very close to 1, and we have a very large number of statistically independent parameters for each of these two fittings. So this is for the weak priors and this is for the strong priors. What we see essentially is that the marginal posterior distributions of the parameters are nearly identical for both set of priors, which means that the change in the prior does not affect the posterior distributions. This is what we have done is known as the prior sensitivity analysis and should be done on a routinary basis for Bayesian statistics whenever we don't have strong defensible priors that we can define in a model. So because the priors are always a point open for discussion in Bayesian statistics, we should always aim to check whether the chosen priors have an influence or not on the posterior distribution that we have obtained. Since here we have essentially the same posterior distribution, we are going to focus on one of them. Either would do to continue the analysis. So the posterior distributions is we are now seeing that the three chains converge to the same marginal posterior distribution for each of the parameters. The degree of mixing of the chains are pretty good. None of the chains got stuck in a narrow range of the parameters for a large number of iterations. All the three chains explore the same ranges, which is what we mentioned in Bayesian statistics as very good degree of mixing of the chains. The parameter estimates retained in the chains are all essentially statistically independent, which is another sign of a very good fitting model. So we assess the goodness of fit of the data using the Pearson residuals as usual, and we see essentially that when plotting the residuals against the fitted value, forget these two points. We have a random scatter here for the overwhelming majority but two of the points, and that the scatter is nearly the same in the positive and negative sides of the residuals. When we compare the residuals against glucose, we essentially see that the median of the residuals between these two groups are nearly the same, which is a sign of a very good fitting model. These two worrying residuals are essentially the same as here. That the model has the residuals follow a normal distribution with the exception of two of the points. Again, so the model has a pretty good fit to the data. To communicate the results, we first notice that the model explains a very large proportion of the variation of the response variable, 93.2%, with a credible interval, 95 credible interval ranging from 91.7 to 93.9, which is extremely precise. So we obtain the curves relating the cell diameter against the culture concentration, and we obtain the expected results. Two roughly parallel curves between the two levels of glucose, and the 95% credible intervals show us the mean of the posterior distributions. In dark blue the 50% credible intervals, and in light blue the 95% credible intervals. The three parameters for which we don't see the intervals is because they were extremely precise and cannot be seen in the same plot. So in this video I explained the analysis of covariance, starting as usual with the exploratory data analysis to be followed by the frequencies fitting and the Bayesian fitting. The codes are all in this website as well as the data. So I hope you found this video interesting. Thank you for watching it.